Suppose that circles of equal diameter are packed tightly in n rows inside an equilateral triangle. See the figure below where the case n equals 4 is shown. Let P sub n be the picture showing the n rows of circles, and let A sub n be the total area occupied by the n rows of circles. Part A asks us to show P sub 1, P sub 2, and P sub 3, and then compute A sub 1, A sub 2, and A sub 3. Part B then asks to now compute A sub 4. C asks to determine a general formula for A sub n. Part D asks us to find the limit of n goes to infinity of A sub n. Part E then asks us to explain the significance of the result in Part D. For instance, how much of the area of the triangle will the rows of circles eventually occupy to the nearest percent as n goes to infinity. For Part A, we need to draw a representation of P sub 1, P sub 2, and P sub 3 with triangles with 1, 2, and 3 rows of circles inscribed within them. We can see that here in P sub 1, there is 1 row of circles and 1 circle inscribed in the triangle. P sub 2 has 2 rows of circles and 3 circles inscribed in the triangle. And P sub 3 has 3 rows of circles and 6 rows of circles inscribed in the triangle. Next, it asks us to find A sub 1, A sub 2, and A sub 3, where the areas of the triangles P sub 1, P sub 2, and P sub 3 based on the area of the circles inscribed in each triangle. Or put more simply, it is the number of circles inside of the triangle multiplied by the area of the circles. So for P sub 1, there's 1 circle. We multiply that by the equation for the circle, pi times r squared. For P sub 2, we have 3 circles. We multiply that by the area of the circles, which is pi r squared. So 3 times pi r squared. In P sub 3, we have 6 circles. Multiply that by pi r squared. Part B then asks us to compute A sub 4. We have a drawing here of A sub 4 with 4 rows of circles and 10 circles inscribed inside of the triangle. The equation then is just the number of circles, 10 in this case, multiplied by the equation for the area of a circle, pi r squared.
Part C asks us to find a general area formula, A sub n. We can start by saying A sub n equals b times pi times r squared, where b is the total number of circles inscribed in the triangle, also known as the summation of n. If the summation from one n is given as 1 plus 2 plus 3 plus 4 plus n, then we can have the summation of n as the average of the first and last values, n plus 1 over 2, times the number of values being added, n. So b equals n times n plus 1 over 2, and a sub n equals n times n plus 1 over 2 times pi times r squared. Now we need to find a sub n in terms of a single variable n. To do this, we need to find a value for r in terms of n. We can do this by finding an equation for the length of the base of the triangle, L, in terms of r and n, assuming L is a constant. We can find the length of L in terms of the radii of the bottom row of the inscribed circles. Let's start with the 2 circles on the end of each row. From this, we can see that each of the following right triangles have height r. The hypotenuse of this triangle is the line that will bisect the angle of the equilateral triangle and intersects the center of the circle. This gives us a 30, 60, 90 right triangle. The base of 30, 60, 90 triangle is square root 3x, the height is x, and the hypotenuse is 2x. But in this case, our x is r. So our triangle is square root 3r, r, and 2r. The remaining length of L in terms of r can be seen above. 2r is the length given by each of the circles that are not at the ends of the bottom row. Since there will always be 2 circles at each of the bottom row, the number of circles that will be between the end circles will be given as n minus 2. That means the length of the base of the triangle given in terms of r by the 2 end circles is 2 times root 3r plus r. Therefore, L equals 2 times root 3r plus n minus 2 times 2r. Now we can solve for r in terms of n. First, factor out an r from all terms on the right. Now divide both sides to solve for r. With our equation for r, we can substitute this value into our equation for a sub n. A sub n now equals n over n plus 1 over 2 times pi times L over 2 root 3 minus 2 plus 2n squared.
Part D asks us to take the limit of a sub n as n approaches infinity. We can start by writing the limit as n approaches infinity of n times n plus 1 over 2 times pi times the quantity L over 2 root 3 minus 2 plus 2n squared. Next, we can distribute the exponent and distribute pi to the first fraction. This will give us the limit as n approaches infinity of pi n squared plus pi n over 2 times the quantity L squared over 2 root 3 minus 2 plus 2n squared. We can then multiply out the denominator of the second fraction. This will give us the limit as n approaches infinity of pi n squared plus pi n over 2 times L squared over 4n squared minus 8n plus 8n root 3 minus 8 root 3 plus 16. We can then combine like terms and as well as combine the two fractions together. This will give us the limit as n approaches infinity of pi n squared plus pi n times L squared over 32 minus 16 root 3 plus 16n root 3 minus 16n plus 8n squared. If we take the limit of this, we can see that the result will be an indeterminate form of infinity over infinity. In order to find the actual limit, we can use L'Hopital's rule. After applying L'Hopital's rule, we will have the limit as n approaches infinity of 2l squared pi n plus l squared pi over 16 root 3 minus 16 plus 16n. Taking the limit of this will again give us the indeterminate form of infinity over infinity, so we can use L'Hopital's rule again. This will give us the limit as n approaches infinity of 2l squared pi over 16. Taking the limit, this will give us l squared pi over 8. So the limit as n approaches infinity of a sub n equals l squared pi over 8.
Okay, for part E, we're asked to find what percent of the triangle's total area will be covered by circles as n approaches infinity. And we can find this by taking the limit as n approaches infinity of a sub n, which is the total area of the circles, and dividing it by the equation of the area for an equilateral triangle, which is root 3 l squared over 4. And so we divide that, and using simple algebra, the l squareds cancel out, and it becomes pi over 2 root 3, which is approximately 91%. So the most area that the circles could possibly cover of an equilateral triangle is 91%.